So what's this about? So we are running a background monitoring on our cluster, and we have this web interface that's accessible over jobmon.pc2.upv.de from the university network. So you need a VPN or IDROM, and there you basically see some metrics that are measured during your job runs. So you see the information for your jobs. So it's a background measurement. You don't have to activate it, but you can deactivate it in case if you want to do some benchmarks. And for these benchmarks, you do your own measurements. This may conflict with the measurements of our background monitoring, because then there are some hardware features used for this, and there could be a conflict. But else it just runs in the background, and it has a sampling interval of 30 seconds. So every 30 seconds, it looks at some selected metrics and stores them, so you can get an idea over the time of your job, how it behaved. So your job has to have a certain minimum runtime. After some minute, it appears in the job monitoring system, and then you can even see some live metrics, and it updates every few minutes. Now this is nice. You see some nice plots, but you have to be keep in mind that it's measurements, samples of some metrics on a highly complex system. So we always need to think about what do these plots and numbers mean. They are linked to reality, so something happens in reality, and then also something happens in the metrics, but they are not exactly equal reality. So we always have to interpret how what the behavior of your job influenced the numbers. So you can use the job monitoring to double check some configurations. You can find some obvious performance problems, or monitor your performance for a longer running job to see if it still behaves as expected. If you open up the job monitoring, you see an overview of your account of the monitored jobs, and then a list of your last jobs and an overview of some of the metrics, and then you can basically click on one of the jobs, and you get to the job page, and there you have some basic information about the resources that you allocated. You have a spider plot of the floating point operations, the memory bandwidth, and the used memory. And there is a so-called roofline plot. So this is often used in HPC to plot the floating point operations against the memory bandwidth. And then you see the time series for various metrics for the duration of your job. And at the end, you see some statistics, min, max, average values for some metrics. You can see it here, and some more details about your job. Now, what metrics are available? As you see here in this table, there's a list of metrics, and here's an important part that these metrics are sampled at a certain granularity. So for example, some metrics are per core. For example, the CPU clock. So you will have a value for each CPU core. Some metrics are per socket. So you only have samples per socket. Some metrics are only sampled per node. So this is an important difference, because as you know, your jobs can use a node exclusively, or they can share a node with different jobs. if your job shares a node with a different job, then metric that is at a node level is influenced by the behavior of your job, but also by the job, um, the other job that is running there. It could be another job from you. It could be another job from a different user. The thing is that now you see some values that belong to multiple jobs, and it's not clear if, for example, a high value in a metric is because of your job or a different job. So there, it's very hard to interpret, and it's kind of unusable, or you can get the wrong conclusions from looking at these values. But if your job uses the node exclusively, then the resource is only used by your job, and then yeah, only your job influences this metric, and therefore then you can take a look. So we see here CPU load core. The CPU load is the number of threads in the operating system that is ready to run or is currently executing. So this is a certain metric used by Unix-based systems to think about the load. CPU user is the percentage of time on a CPU core that your user code was running or using this core. So for example, if there's a 50%, then this means that 50% of the last sampling period, the CPU core was used or was running your code. Then we have the floating point operations per second, the CPU frequency, the power draw. And what we also see here is network traffic, which is the raw um, network traffic, but we also have the parallel file system metrics here. So Lustre for Noctua 2 and GPFS for Otus. And these metrics are tied to the network metrics because the parallel file system is a network file system. Therefore, if you do something with a parallel file system, then it will also, you will see some values going up, for example, in the IB InfiniBand network metrics. And finally, the NV metrics are for the NVIDIA GPUs that we have on the GPU nodes. Now let's take a look at a basic example. It's a good idea to first look at an idle system. So how would an idle system look like? So we are running a basic enterprise Linux system on our cluster, and most metrics are basically near zero. Um, the For example, the CPU load, we are running no threads that want to compute something, so there's no load, and the CPUs are not used, so no percentage of the time is used by your code because no code is running, and also the memory is at a certain uh, base value because this mem used metric includes some of the operating system memory. So there's always an offset here. And in the clock, you will see varying clock values, but often they are also kind of low at the base clock, because also when idling, then when the CPU core is idling, that can interfere with the measurement. And the package power on auto system here is between 40 and 50 watts. So you see here the two lines. There's a certain offset between the two sockets, but this is basically when nothing is happening. So we see here in this example there is some The IPC values, maybe some daemons of the operating system in the background executed something, but that's not dramatic. And we see some values here in the networking, but they are only, I know, a few packets per second. Now we can think about what happens if one thread is doing something. In this case, this example is a while true loop in bash that is not printing anything. It's just looping through these instructions but not doing anything, and that's basically integer workload for bash. It is running on one core, so we have a load of one, so it's next to nothing. And we have here in the load per core metric, we have a value of 1. And we see there's a certain ramp up phase, 5 minutes or 1 minute per CPU load core for the load, because it then depends on if what happened before your job on the system. So it influences a little bit the first samples of these measurements of your job. And here you see that apparently this thread jumped a little bit between cores. So there are different colors here in the CPU load core, and also in the CPU user. There's always one core that has 100% value. Flops are 0 because this workload is not doing any floating point operations. And we see that the busy core goes up to 4.5 gigahertz, and the other cores are basically similar to when they're idling. And the package power is a little higher than an idling value, maybe plus 15 watts. And we also see here how the thread switched sockets, and because this metric is per socket, then we see here a certain change. Now this was an example for one thread that is not doing any meaningful computation, but we can also look at synthetic benchmarks. So these benchmarks are basically allocating a little bit of memory and then doing some instructions in a loop. And these are not really meaningful calculations. They are just executed to see how fast can the CPU execute some instructions, basically, and how many floating point instructions can we per second can we achieve. So this is done using Liquid Bench, and Liquid is a suite of tools to do measurements and benchmarks on CPU systems. So here we see some the peak flops benchmark on AVX 512. So they are using this SIMD feature to do the operation, execute operation on multiple values at the same time in a vector vectors, and we are doing fused multiply and add operations. Therefore, per instruction, we are doing one multiplication and an add, because then we can basically count 2 operations per instruction. And here are some values for double precision and single precision, 2 different benchmarks. So we have a very small data set. It fits in the cache. Therefore, it's also not talking to the main memory. So it's basically just instructions in the CPU, and we see how does it influence our metrics. Let's start with one thread. We are doing this benchmark on one thread, and we can achieve 144 gigaflops on the busy core. And we have a higher IPC instructions per cycle, and we see that again the clock goes up to 4.5 because the only one thread is executing something and the other cores are idling. Therefore, on the core that the thread is running on, this can be clocked very high to 4.5 gigahertz, and the other cores can have a low frequency. And the package power is a little bit increased. Well, little, it's quite increased to support the workload that is happening on this one thread. And what we can also do is we can run the workload on all of the threads. So the same thing in parallel on all of the 192 threads. And what we see here is that package power is way higher. It's using a lot of power to do the calculations. But the clock is lower because now all of the cores are busy. All of the cores have to clock up, or you want them to clock up to have a better performance, but they can't clock all up to 4.5 gigahertz at the same time because the CPU can't draw more power to power all of the cores at the same time. It's basically capped by how much power it can take in. And therefore, the CPU has to clock down the cores. And we have, because of this, because the peak or the frequency is lower, we also have slightly lower performance per core, only 112 gigaflops per core instead of the 144 gigaflops on 4.5 gigahertz. But still, if we add all of this up, it's worthwhile because we are doing this computation on all of the 192 threads in parallel. Now, these numbers are basically what the CPU is capable of in a synthetic benchmark if the application is not doing any, not much memory accesses. So basically, it's just a thing how large the numbers we can get if we do any instructions on the floating point instructions on the CPU. But you basically won't achieve these numbers in your typical application because, for one thing, your application consists of not only this mix of instructions. It's not only doing floating point instructions. It's also doing control flow, loading, writing of data, and so on. So yeah, this limits the floating point number. And also there's you have to consider all of the memory accesses that your real application is doing. So it basically can't reach these synthetic numbers. But it's interesting to see what is the peak performance of these CPUs. And we can also do it with the memory bandwidth. So this is load AVX benchmark, and here we're only doing loads from the memory. And we are doing this in this example with a certain number of threads. And what we, so again, in a small loop, we are doing repeated memory transfers or reads from memory. And as we can see here on one thread, we can achieve 50 gigabytes per second and a little bit more. Again, the power draw is increased, and but with 24 threads, we can already achieve a good memory bandwidth per socket. But as we see here, because now more threads are active, also the power draw is way higher, and also with, for example, 48 threads onto sockets. We can compare these 290 watts per socket with a 320, and we see the kind of instructions that you're executing have impact on how the CPU is operating. So here we basically only have memory accesses, and the memory system is used by the CPU, and then it draws less and clocks higher than if you would use the floating point operation execution units on the CPU that do all of these calculations and then draw more power. in total. Now let's take a look at some pathological cases. In our first example, it's core oversubscription or underutilization. This means, as we've seen before, you would think how many threads should I run on one core if you configure your application, and a good value would be 1 thread per core, because then the thread is not interrupted. So if 2 threads share a core, then it's a time sharing of the core, and then basically the first thread has to stop being executed, and then the second thread starts, and then it, for example, also sees maybe a cold cache, so it has to load the data from main memory again, and so it has again a little ramp up phase and so on. So it's not as efficient as if the thread would simply continue running on a core. And this behavior is even worse if the more threads you have on running per core, and also there's the scheduler also takes some time to decide and to switch between the threads that are sharing a core. So you can see here some pathological cases. Here we have 2 threads per core, and the CPU time is still all right. In this case, we have 16 threads per core. It doesn't even show on the plot anymore. And we see that we have a strange behavior in the CPU user time, because this is only the percentage that your user code was running on the CPU, but here is also something else going on. So maybe the operating system took some time on average on the CPU just for the scheduling of multiple threads. So you can see here in the total number of threads on the system for Noctua 2, it would be 128, because you have 128 cores, and on Otus it would be 192. So this is when you run more threads than you have cores. There's also the opposite case when you are reserving, for example, a complete node, but then your application only uses, let's say, 5 cores, only runs 5 threads. Then you have allocated a lot of resources, but you are only using a very small amount of these resources. So that's also bad. These resources in this time could be used by some other user, or maybe even by a different job of yours. So this is when you reserve more cores than you are using. There can be good reasons to do this. For example, if your application uses a lot of memory, for example, the complete memory of the node, but doesn't use all of the cores for computation. This can happen, but usually this is not the case. And you can look out for this, and if there's not much happening, there's a low utilization of the CPUs, then maybe there's something going on. Another example is memory leaks. So here the used memory rises with time because of the memory leak. There is memory allocated, but then it's not used any longer. It is forgotten by the application. So it's still reserved in the system. And this can, in the end, lead to a out of memory error if your job is using more memory than it reserved on the system. And you can spot this by certain increase of memory, of used memory over time. So often it's a little bit of memory that is leaked in a loop, for example, and then with time it just sums up all of this leaked memory. And this may be not a problem if your job exits before it runs out of memory. But it could be that it's fine for now, but if you decide to increase the simulation time of your application, then it could become a problem because then you could run in out of memory error later in a different job. And on the other hand, this could also be expected behavior of your application. For example, during your simulation, the application is programmed in a way to store some data in memory over time, then you would also see this kind of behavior. So it depends on if this is normal behavior of the application or not. Next case is repeated reads from the network file system. In this example, we have a simulation that regularly reads and writes input files or temporary files, and it stores or reads these files from the network file system. So it can be just the way the application is written, but maybe you can do something about it. Now the problem is um, here you see these regular um, patterns in these metrics here. So there's kind of a simulation loop, and there's always going something on, and you see some larger values in the network metrics or the here in the network file system metrics. Here regularly you see these larger values in reads or file accesses. And maybe you can improve this by first copying the input file to the um, in-memory file system on the node. So under /dev//shm, you can copy some data, and this will be stored in the main memory of the node. And if you regularly need to read this data, then it will be read from the main memory and not from the network file system. This is way faster, and um, also it reduces the load on the network file system for other users, because in this case the network file system is stored on the central storage of the cluster, and therefore the load is then sums up from all of the jobs of the users on the cluster. So using this trick, you can not only reduce the load on the network file system, but also improve the performance of your application, because reading from main memory is way faster. And this is also true for temporary files in /temp. On the normal nodes /tmp is backed also by the parallel file system. So there's the same behavior basically. Now let's get back to our n-body example from the last section. So what is happening at this place in our scaling analysis? So what we can do is we can compare the metrics. So here we see a grid of these metrics. So we have 3 rows for the floating point operations per core, the memory bandwidth per socket, and the transmitted or sent packets on the network per node. And we have 4 columns. We have the experiment with 1 node and 1 rank, 1 node and 128 ranks, 2 nodes and 256 ranks, and 4 nodes and 512 ranks. So in our first experiment, we only using 1 rank or 1 process for simulation, and we achieve 18 gigaflops on one core, and we see no network usage or no real memory bandwidth usage here. Now, when we increase it to 128 ranks on Octa 2, these are then one full node. We see that the performance drops to 9 gigaflops. This can also be a little bit because of the reduced frequency. But we also see here we have a little increase also in the memory bandwidth. Then when we switch to 2 nodes, the performance drops to 5 gigaflops per core, and we see now an increase in network usage because now the 2 nodes have to talk to each other for the simulation. And we then go to 4 nodes, an even higher drop and even more network usage. And we see that especially one of the nodes sends a lot of packets, and all the other nodes send less packets. So 1.5 million against 40,000 packets per second. So we can see for the simulation, the ranks have to communicate, talk to each other, and this communication behavior influences the performance. And as we see here, when we switch to 2 nodes, the performance drops. The more nodes we are using, the more communication has to go on. And we see here also that it seems one node does communicate more than the others, so there's a asymmetry in the communication in this application. So we can see that the communication between the ranks takes up basically all of our speed up that we could have gained. And as explained, if we the communication implementation could be improved to produce less overhead, to have maybe a smarter communication patterns, then this can increase the performance and the possible performance and the scaling behavior of our application. Now we're coming to an end, and there are some other tools that you can use to inspect your jobs. While a job is running on the cluster, you can SSH into the node that your job is running on. So you can do this to monitor them or to debug your application. So with SQ, you can figure out the node name that your application is running on. Then you can simply do SSH into the node using the node name if you're on the login node. And then you can, for example, open HTOP and look at your processes and see what they are doing. You can also use the SEFF tool to see some very rough metrics for CPU memory utilization. So it's you can do a very rough sanity check, but you have to be careful because high numbers, high utilization doesn't mean that your application is running efficiently. It can also, for example, be that just CPU time is high and your job is stuck in a busy waiting loop, for example, or you can still have a oversubscription. And finally, if you want to go deeper into performance analysis of your application, there are further tools, for example, Liquid, as we've seen, to do some experiments and do some measurements of very other specific metrics that are available on the CPU. You can also use Intel vTune or AMD UProf to do some analysis and check some hardware performance metrics to see what the CPU is doing, how your application behaves. And you can even do this for specific code regions, not for the complete application.